Hello friends, welcome to EC Academy. In this lecture, let us understand frequency domain sampling and reconstruction of discrete time signal. To analyze a discrete time signal, this discrete time signal should be converted into equivalent frequency domain representation. This equivalent frequency domain representation is known as Fourier transform, which is represented as x of e to the power of j omega. So to analyze a discrete time signal, this discrete time signal should be converted into equivalent frequency domain representation. This frequency domain representation is known as Fourier transform, which is represented as x of e to the power of j omega. But frequency domain representation is not convenient representation for a discrete time signal. So discrete time signal can be represented as x of n. So the frequency domain representation is not convenient for discrete time signal. Hence the Fourier transform is sampled to obtain a frequency domain. So Fourier transform x of e to the power of j omega is sampled to obtain a frequency domain sequence x of k. This sequence is known as discrete Fourier transform. X of k is known as discrete Fourier transform. This discrete Fourier transform is powerful tool to perform the frequency analysis of a discrete time signal. Hence we will go with DFT to perform the frequency analysis of a discrete time signal. Now in this topic we will establish a relation between Fourier transform and discrete Fourier transform. So Fourier transform is represented as x of e to the power of j omega. Discrete Fourier transform is represented as x of k. Now let us consider a non-periodic discrete time signal which is represented as x of n. Now the Fourier transform of x of n can be represented as x of e to the power of j omega. Now we can write the Fourier transform of x of n as x of e to the power of j omega, which is same as x of omega, can be written as summation of n is equal to minus infinity to infinity x of n e to the power of minus j omega n. Let us call this as equation number 1. So this is the Fourier transform representation of x of n. Here x of e to the power of j omega is periodic with fundamental frequency ranging from 0 to 2 pi. Here omega is fundamental frequency. It is ranging from 0 to 2 pi and the unit for omega is radians. Here omega is a continuous function. Now let us graphically represent x of e to the power of j omega. So here omega will be in x axis and in y axis we will take x of e to the power of j omega. We have a continuous signal and this omega is ranging between 0 to 2 pi. So after each interval 0 to 2 pi the signal will be repeating. So this is towards right hand side, towards left hand side it will be minus 2 pi. So 0 to minus 2 pi, here 0 to pi. So this is the graphical representation of x of e to the power of j omega. Now let us take n equidistant samples in the interval 0 to 2 pi. For omega value 0 to 2 pi, we will take n equidistant samples. So we'll take a sample here, second sample, third. Likewise, we'll take the sample up to n minus 1. If you take n samples, we'll write from 0 up to n minus 1. If you start from 1, you can take it as 1 to n. Since we are starting from 0, we'll take up to n minus 1. Now the width of each sample is represented as delta omega. Delta omega will be equal to 2 pi by n. So here we are writing the sample space as 2 pi by n because the range is up to 2 pi and we are taking n samples. That's why we are taking the sampling space as 2 pi by n. Using this analysis, in equation 1, we will replace omega by 2 pi by n into k. So we will replace omega by 2 pi by n into k. So here we are taking k with a range 0 to n minus 1. For k, we are taking the value as 0 to n minus 1. So here, if we take k is equal to 0, at that case, the above equation will be 0. That will be representing the sample that is present at 0. If we take k is equal to 1, at that case, the above equation will be 2 pi by n. So from 0, the distance here it will be 2 pi by n. So that will represent the first sample. If we take k is equal to 2, at that case the above equation will be 4 pi by n. So from 0 up to here the distance is 4 pi by n. That will represent the third sample. Likewise up to n minus 1, so it will represent individual samples. So we can say the term k provides the value of individual samples. Now if we replace omega is equal to 2 pi by n into k in equation 1, so we can write x of 2 pi by n into k is equal to summation of n is equal to minus infinity to infinity x of n e to the power of minus j. Instead of omega we will write 2 pi by n k n for k value ranging from 0 to n minus 1. Let us call this as equation number 2. If we observe this equation, this term represents the summation from minus infinity to infinity, which means it is having infinite number of summations. So we can say x of n is having infinite number of summations. So we can expand the above equation and we can write x of 2 pi by n into k is equal to, we know x of n is having infinite number of summations with n samples. For n samples we can write from 0 to n minus 1. So we can write summation of n is equal to 0 to n minus 1 x of n e to the power of minus j 2 pi by n kn plus, we can write next summation. So for this we need to add n samples. So for 0 if we add n samples we will get n is equal to capital N. For this if we add n samples it will be 2n minus 1 x of n e to the power of minus j 2 pi by n kn plus and so on, and the summation before to this summation will be summation of, for the next summation we have added n, for the previous summation we need to subtract n. So if we subtract n from this summation it will be n is equal to 0 minus n, it will be minus n. So here if you subtract n in this term you will be left out with minus 1. x of n e to the power of minus j 2 pi by n into kn plus previous values. So this is the expanded version of the above equation or equation number 2. Let us take this equation as equation number 3. Equation 3, I will write it as x of 2 pi by n into k is equal to summation of L is equal to minus infinity to infinity, summation of n is equal to ln plus n minus 1 x of n e to the power of minus j 2 pi by n into kn. Let us call this as equation number 4. Equation 4 is compact version of equation number 3. We have reduced the equation number 3 and we have written the compact version of equation number 3 as equation number 4. Now in this equation, if you observe, L is ranging from minus infinity to infinity, which means L can take the values from minus infinity to infinity. In this term, if you put L is equal to 0, at that case this term will become 0 and here this term will become 0. So we will be left out with n is equal to 0 to n minus 1. So we will get this term. Now if we put L is equal to 1, at that case we will get n is equal to capital N up to 2n minus 1. So we will get this term. If you put L is equal to minus 1, at that case it will be n is equal to minus n up to minus 1. So we will get this term. So we can say equation 4 is compact version of equation number 3. Now let us put n is equal to n minus ln. At that case we can write ln is equal to n minus n. So we can write ln is equal to 0. So in the above equation, let us replace n by n minus ln. At that case ln will be equal to 0. So we can write the above equation as x of 2 pi by n into k is equal to summation of L is equal to minus infinity to infinity, summation of, if you put ln is equal to 0 here, it will be n is equal to 0. Again in the upper summation, if you put ln is equal to 0, it will be n minus 1. X of n is replaced with n minus ln e to the power of minus j 2 pi by n into k. N is n minus ln value is 0. So we will write n. Let us rearrange this equation and we can write x of 2 pi by n to k is equal to summation of n is equal to 0 up to n minus 1, summation of L is equal to minus infinity to infinity, x of n minus ln e to the power of minus j 2 pi by n into kn. Now this term represents the periodic signal with period capital N. So this represents the periodic signal with period N. So we can represent x of n minus ln as xp of n. Since x of n minus ln is a periodic signal, we can replace this term as xp of n. So we can write the above equation as x of 2 pi by n into k is equal to summation of n is equal to 0 to n minus 1 xp of n e to the power of minus j 2 pi by n into k n. Let us call this as equation number 5, and this signal is discrete Fourier transform equation. So this equation is known as discrete Fourier transform equation. So we'll discuss regarding this equation in the next classes. For time being, remember that this equation represents the discrete Fourier transform equation. Using Fourier series, any periodic signal can be represented as xp of n is equal to summation of k is equal to 0 to n minus 1 ak e to the power of j 2 pi by n kn for n value ranging from 0 to n minus 1. So this is the periodic signal representation using Fourier series. Here ak can be written as 1 by n summation of n is equal to 0 to n minus 1 xp of n e to the power of minus j 2 pi by n into kn for k value ranging from 0 to n minus 1. Let us call this as equation number 6 and this as equation number 7. Here ak is Fourier coefficient. Now let us compare equation number 7 and equation number 5. Let us compare equation number 7 and equation number 5. So if we compare equation 7 with equation number 5, this term is same, so we can cancel out these two terms and we will be left out with ak is equal to 1 by n and x of 2 pi by n into k. So using these two, we can write the value of ak is equal to 1 by n into x of 2 pi by n into k for k value ranging from 0 to n minus 1. Let us call this as equation number 8. Now let us put the value of ak in equation number 8 in equation number 6. If you put the value of ak in equation number 6, we can write xp of n is equal to summation of k is equal to 0 to n minus 1. Here instead of ak, we will write this term which is 1 by n into x of 2 pi by n into k e to the power of j 2 pi by n kn for n value ranging from 0 to n minus 1. Now let us take 1 by n outside the summation and we can rewrite the above equation as xp of n is equal to 1 by n summation of k is equal to 0 to n minus 1 x of 2 pi by n into k e to the power of j 2 pi by n kn for n value ranging from 0 to n minus 1. Let us take this equation as equation number 9 and this equation represents inverse discrete Fourier transform equation. So equation number 5 represents discrete Fourier transform equation. Equation number 9 represents inverse discrete Fourier transform equation. Remember this equation, we will discuss regarding this in the next classes. Now equation number 9 gives the reconstruction of periodic signal from the samples of Fourier transform. You can see we have reconstructed a periodic signal from the samples of Fourier transform. So we can write equation 9 gives the reconstruction of periodic signal xp of n from the samples of Fourier transform x of e to the power of j omega. This topic is very important for the exam. This is about frequency domain sampling and reconstruction of discrete time signal Hope you have understood the topic. Thank you.